we will now see before we go to demodulation of frequency modulated signals, there's one small thing I want to stress on the frequency modulated signals as such. Now, just some time back, you have seen the spectrum of FM signals. I had a carrier frequency of 500 kilohertz and I had a single message signal with a single frequency of 20 kilohertz, and with that we showed you how frequency modulated signal looks like in time domain, and we've also seen the spectrum of the frequency modulated signal. Once again, we will show you on the screen. This is the spectrum of the frequency modulated signal. Now, we can ask a question whether it is possible for me to find out the modulation index by looking at the spectrum of the FM signal. If you look at carefully, this central peak that we are seeing here is basically the carrier. That is at 500, the marker is located at the central peak, and central peak is about 501 kilohertz. That's the carrier frequency. It is possible for me to find out the modulation index beta if I look at the carrier frequency. Now remember that this beta is related to the peak message signal amplitude, the amplitude of the message signal. Now, if I change the amplitude of the message signal, if I increase it, what will happen is that this beta value will change. Now this is J0 beta. If you look at the Bessel function representation of FM signals, this is J0 beta. As I change the beta value, what will happen is the carrier power will begin to drop. Number of sidebands would increase, the carrier power would begin to drop. There will be a particular value at which the particular value of message signal, amplitude of message signal, where the carrier power would go to the first null. That is, the carrier power will go to 0. The position at which carrier power goes to 0, that's the first carrier null. One can find out the value of beta. Beta at this value will be 2.4. Then, if I continue to increase the message signal amplitude, the carrier power will then begin to rise. It will reach a peak, again it will begin to fall, and it will go towards the second null. Second null happens at a value of about 5.4 or so. So by looking at the first null, second null, third null, and so on, I can find out the value of beta. At these values of beta, J0 beta will be equal to 0. We'll just see that. Now we want to increase the amplitude of the message signal. Just know how this peak will slowly fall down. See, now what has happened, the first sideband on either side of the carrier has come down, the carrier power is reduced. Now if I go on increasing the message signal amplitude, the carrier power will reduce further and further, and it will go towards the first carrier null. So I can find out the value of beta by looking at the spectrum of this. The spectrum has become wide because I am using a larger value of beta, at the same time the carrier power has fallen down. The spectrum becomes wider at the expense of carrier power. As the carrier power falls down, the spectrum becomes wider and wider. This is a characteristic of angle modulated signals, the frequency modulated signal. Now, we will, having carried out frequency modulation, we will now see how do we demodulate a frequency modulated signal. Now, before we understand demodulation, we must understand what did we do at the modulation side. At the modulation side, the message signal amplitude varied and the voltage control oscillator's frequency varied in proportion to the message signal amplitude, in proportion to the message signal. So as the message signal increased, the frequency deviation increased, the instantaneous carrier frequency went away from the instantaneous frequency went away from the carrier frequency, it went towards higher frequencies. As the message signal reduced in amplitude, the carrier frequency became, the instantaneous frequency became Fc minus that part kf by 2 pi times mt. Okay, so Fc minus, because mt now is negative, it is falling, it is Fc minus that quantity. So that is how the instantaneous carrier frequency increases and reduces around the carrier frequency, and therefore what am I doing? The input voltage variations are being mapped to the changes in the carrier frequency. That is what is happening in the transmitting side. At the receiving side, I need to do the reverse operation. That is, I need to track the change in the carrier frequency and map that to voltage changes. So the demodulation is exactly the inverse process of modulation. So in the modulation side, by looking at the message signal variation in the amplitude of the message signal, I map that to the variation in the carrier frequency. On the demodulation, on the receiver side, I must do the inverse operation, that is, track the changes in the frequency of the carrier and map that to voltage variations. So by doing that, I would have recovered whatever signal was impressed on the carrier. You must remember that the message lies in the frequency of the carrier. It is hidden, it is encoded in the frequency of the carrier. So by tracking the frequency of the carrier, you can recover back the message signal. Now there are different ways you would learn in the class, or you have probably learned in the class by now. There are different ways of demodulating FM signal. Now one popular way, of course, is by using phase lock loop. One can also use what is called as a Foster-Seeley discriminator. Now before we go to demodulating the signal using Foster-Seeley discriminator, let me just explain to you the circuit. Now this is the circuit diagram of a Foster-Seeley discriminator. Now this is basically an intermediate frequency transformer. Okay, we call it as IFT, intermediate frequency transformer. To the input of this, now this is the primary side, this is the secondary side. Now what you should notice, the secondary side is center tapped. Okay, the primary side is where I would feed in the FM signal. On the secondary side, this is center tapped. The top half of the transformer and the bottom of the transformer have voltages which are equal in magnitude, but they are opposite in phase, that is, they differ by 180-degree phase. Now when I am at the carrier frequency, now what am I going to do? I am going to input the FM signal. The FM signal is going to have a variation in frequency. So the input is frequency, the output is mapped to voltage. So I need a frequency to voltage conversion here. So when I am at carrier frequency, I choose my capacitances in such a way, the CC, C1 and C2. These capacitances are chosen in such a way that at intermediate frequency, these capacitances are short circuits. Okay? When that happens, what happens is that the voltage across R1 and voltage across R2 are equal, but they are opposite in sign and they cancel out. Okay? So the voltage is 0 at this position. Now, if the instantaneous frequency is greater than the carrier frequency or less than the carrier frequency, what will happen is one of these two voltages will be larger than the other voltage. So what am I doing here? Depending on whether I am here or on this side, I will have this voltage more than this voltage or this voltage more than this voltage, and therefore my output voltage I will be in the position to recover the message signal. So that's how I do a frequency to voltage mapping. The changes in carrier frequency have been mapped to the changes in the voltage. By doing that, I would have recovered the message signal. Now let us go to the circuit. Now this circuit that is located here is basically a Foster-Seeley demodulator. I am not in a position to show it very clearly, but I can just show you that this is a circuit for the Foster-Seeley circuit to demodulate frequency modulated signal. At the output of this circuit, I must be able to recover back my original message signal. So we will try to do that. There is a lot of distortion in the circuit, basically because it has got to do with the quality of components that are used in the circuit. But nevertheless, you notice here the frequency is being measured as about, it's trying to measure the frequency, and the frequency is about 20 kilohertz. So I have roughly recovered back whatever message signal I transmitted, though there is a lot of distortion in the amplitude, but the frequency that is being denoted here is about 20 kilohertz. So this is how I demodulate an FM signal. I can use a PLL, I can use a variety of different methods by which I can demodulate FM signal. Many of those methods will be covered in the class or might have been covered in the class by now. Now we will demonstrate to you some interesting features about digital signals. So far you have seen analog signals. Now digital signals are distinctly different from analog signals. Analog signals are continuous signals and they can occupy amplitudes from minus infinity to plus infinity, but digital signals have discrete amplitude levels. So now we're going to talk this demonstration as well as the next demonstration will be only on digital signals. Now how do you get digital signals? If you have computers or microprocessors, they will naturally give you digital output. Alternatively, if you have analog signal, it can also be turned into its digital equivalent. I can do sampling, quantization and convert an analog signal to a digital signal. Now when I have a digital signal, normally talk in terms of bits, binary digits, zeros and ones. So assuming that I have done the sampling and quantization, and let us assume that I have a device which is converting an analog signal to digital signal. At the output of this device, I have zeros and ones available to me. A 0 might denote a negative voltage or a 0 voltage. A 1 will denote a plus 5 volts, let us say, for example. Now I have various, now this demonstration is about line codes, okay. Now these are line codes, various line codes which are also called as PCM formats. Now this is the digital data I am trying to send. This is a string of ones and zeros. So digital data I have is 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1 and so on. Now I can transmit these zeros and ones in a number of ways. I can transmit it using NRZ-L, NRZ-M, NRZ-S. I can transmit this as unipolar RZ, bipolar RZ. I can transmit it as RZ-AMI. I'll explain to you what these abbreviations mean. Now these are the various line codes which are possible. Now NRZ means non-return to 0, and the last alphabet that you see, L, M or S, indicates line, mark and space. Now this line, mark and space are all telegraphic symbols which we derived from telegraphic notation. Line codes were in earlier times were used popularly in telegraphy. Now when I am transmitting a binary symbol, a binary digit by NRZ waveform, NRZ by definition means non-return to 0. On the x-axis here I am marking time. So each of these vertical lines which you see denotes a bit period. So when I am transmitting a 1, and if that 1 occupies the entire bit period, then it is an NRZ line, that is non-return to 0. A 0 would similarly occupy the entire bit period, a 1 would occupy the entire bit period and so on. So this is the way I will transmit a non-return to 0. Now when it is non-return to 0 mark, a mark means 1, a space means a 0 in telegraphic language. Now what does this mean? This is also non-return to 0, but there will be a transition whenever I encounter a 1. So there is 1 being transmitted here, okay. Now next time the next bit is 0, so there is no transition. The moment I encounter the next 1, there should be a transition, that is I am going from a high state to low state. Next bit, the fourth bit is again a 1, so there should be again a transition from low state to high state. So I continue to be in high state as long as I do not encounter a 1. The moment I encounter a 1, my state will change. Either I go from high to low or low to high. So that is NRZ mark. NRZ space is similar to NRZ mark except that the transitions occur when you encounter a 0. So NRZ space, I am denoting 1 by negative voltage. The next bit is 0, so I must have a low to high transition. So I have a low to high transition. I continue to be in a high state till I encounter a 0. The next 0 is coming at this position. So I have accordingly, I have a transition. So wherever you encounter a 0, there will be a transition from low state to high state or high state to low state. That is NRZ S. Now whether it is NRZ L, NRZ M or NRZ S, you should remember that the bit period is completely occupied. Okay. On the other hand, I have something called as unipolar RZ, that is unipolar return to 0. Here, a bit period, a 1 occupies only half the bit period. Okay. So 1 is occupying only half the bit period. A 0 is 0 as such. So wherever there is a 1, I only occupy the first half of the bit period. So that is unipolar RZ. Unipolar because there is only one polarity, 0 and +1. Bipolar RZ. Now there are two polarities here, +V and -V. Now here what I do is, I again occupy only one half of the bit period. I signal a 1 with a positive voltage, I signal a 0 with a negative voltage. Okay? Accordingly, I occupy the first half of the bit period. So I signal a 1, I signal a 1 with a positive voltage, which occupies only half the bit period, and I signal a 0, which occupies a negative, which is indicated by a negative voltage. Again, it occupies only half the bit period. Now this is return to 0 alternate mark inversion. What does this mean? Alternate mark inversion would be alternate mark inversion. That is, every time I encounter a 1, the polarity of that 1 would depend upon what was the previous polarity. Now let us say this is, now again this return to 0, so I will occupy only half the bit period, but a 1 here is a positive voltage. The next time 1 is occurring is at this point, but because this was positive, this will be negative voltage. And because this is negative, the next one will be a positive voltage. It will go on like that. So this is return to 0, alternate mark inversion. Now this is biphase L, biphase M, biphase S. Again, L, M and S have the usual meaning that I explained to you in the talk 1. Now in biphase L, what happens is that again a 1 occupies the first half of the bit period, a 0 occupies the second half of the bit period. Okay? So 1 occupies the first half of the bit period, a 0 occupies the second half of the bit period, and that's how I signal the biphase L. For a biphase M, I occupy either the first half of the bit period or second half of the bit period depending upon how many 1s I encounter. Okay? So when I encounter a 1, I will switch from, now let's say this is the first bit, I am occupying the second half of the bit period. A 0 is signaled as 0. Now there is a second one coming here, but because I occupied second half of the bit period, now I will occupy the first half of the bit period, and I come to the low state. Now this is similar to return to 0. I am coming to a low state. Now there is a 1 here, I must again change my state. I will go to high state and come to low state. And because I was in low state here, the next 0 I must signal with the high state. So there is a transition that is happening at every bit interval. At every bit interval there is a transition happening. Biphase S is similar to biphase N, and I can transmit the information in the following manner. And there are delay modulation, dicode modulation and dicode RZ. They are similar PCM waveforms. Now what you should notice in all these waveforms is the shape of the waveform is rectangular in nature. If I am talking about the spectrum of this waveform, all of you know that a rectangular waveform will have a spectrum of sine square x by, or sine x by x whole square, or sin square x. So the power spectrum of all these waveforms will be sin square x waveform, but they will vary in their bandwidth and their typical features. Now when I look at a waveform, what are the various characteristics I look for? Now the various characteristics I look for are these characteristics. Now what are the various features of the line code? I must look for whether a line code has a DC component or not. I must look for self-clocking information. I must look for how much is the occupied bandwidth. I must look for whether one particular waveform is more immune to noise or less immune to noise, and so on. So here we have a small kit which generates various PCM formats. So this is the small kit I have. There is a clocking circuit, and there is a circuit which generates the data. So the clock and data are given to this line code modulator. At the output of this, I get variety of line codes. Now what I am showing you on the screen now there are 3 traces I am showing you. If you remember, I talked in the first demonstration when I talked about the instrument, I told you that there are 2 analog channels and 16 digital channels. Now because this is a digital data, I can use digital channels here. Okay, so I am not connecting anything to these 2. I am connecting only to the digital channel. And what I am displaying on the screen are digital data. I have 3 channels here. Out of 16 channels, I am using only 3 channels. The lowermost one is the clock, the middle one is the data, and the top one is the actual line code. Okay? So what I am showing on the screen is a typical waveform of NRZL. So what could be the data here? Now each clock period corresponds to, the data is 1. So this is 1, 1, 1. There are 3 ones in this. Okay? This rectangular waveform, the middle one, stretches to 3 clock periods. So there are 3 ones followed by maybe 3 zeros. There is a single one, there are 2 zeros, and so on. This is the corresponding NRZL waveform. NRZL waveform will look exactly similar to the data. Okay, so this is the way I transmit NRZL waveform. Next is NRZM. In NRZM, my data will have a transition. My waveform will have a transition from high state to low state or low state to high state wherever I encounter a 1. Okay. So for example, if you notice, I have encountered a 1 here. If I am encountering a 1 here, I was in low state, so I must go to high state. Okay. Next, it is 0 here, there are 2 zeros, so I continue to be in high state. At this point, I have a 1. Okay, so I come from high state to low state. There is another 1 sitting next to it, so I go from low state to high state. And there is a 0 here, so I come from low state to high state, and then high state to low state, and then I keep on going like this. Okay, so wherever there is a 1 encountered in the data, there will be a transition from low state to high state or high state to low state. That is NRZM. Next, NRZS. Similar to what I told you earlier, wherever there is a 0 encountered in the data string, there will be a transition from low state to high state or high state to low state. Now here, if you see, there are a string of zeros here coming, maybe about 3 zeros. So there are transitions from low to high state, high to low state. Okay? So high state to low state to high state to low state, corresponding to the 3 zeros that were there in the data. So likewise, you will transmit the NRZS waveform. Now this is unipolar RZ. Unipolar would mean there are only 2 voltage levels. There is only one voltage level. There is a 0 and plus V. Okay. Now look at this waveform. This is my data, and this is the corresponding RZ waveform. Now there are 2 ones, or let's say 3 ones in this, and so the corresponding data is the RZ waveform is here. Let us take this one. There is a string of ones here. So there is a corresponding RZ waveform here. Notice that I occupy only half the bit period, and I come down to 0. Again occupy half the bit period, come down to 0. Again occupy half the bit period, come down to 0, and so on. So this is how RZ waveform would be transmitted. The next is biphase L. Now this is the data, this is the clock information, and the biphase line code is the topmost trace. So here you see the when there's a 0 or 1 occupy the first half of the bit period or the second half of the bit period, and that's how I transmit the biphase line code. Like this, we can have biphase mark and biphase space. Okay, so I have biphase L, biphase M, and biphase S. Now let us look at the power spectral density of these quantities. Now, as I said, these are the important things. The DC component, it's very important. Now, if I am interested in long distance transmission of this data, I must not have DC component. What do I mean by DC component? I'll just show you on the spectrum analyzer. Spectrum, as I told you, since these are all rectangular waveforms, their spectra will be a sin squared spectrum. So this is what you see, the sin squared spectrum. These are the side lobes of the spectrum. Now, what do I mean by saying DC component? Now, this is about 0 hertz. At 0 hertz, I do have some amount of power. If I have some amount of power at 0 hertz, it means that there is a DC component present in the signal. Now, if there is a DC component, what will happen? Suppose I am transmitting this information over long distance. Now, there are repeaters located in a digital communication link. At different locations, there will be repeaters present. Now these repeaters will have transformers inside, and a DC will create a problem at the transformer. DC does not couple to a transformer. So my line code will have a problem for transmission if there is a DC component present in the line code. So this will create problems for me when I am going to transmit this information over a long distance. The next is self-clocking. Now clocking information is very important for recovering at the receiver, or recovering this digital information at the receiver. If the clocking information is lost, then I will not be in a position to recover the information at the receiver. Now supposing there is a string of ones or string of zeros in the data. What happens? A continuous string of ones will tell me it's equivalent to a DC voltage. A continuous string of zeros is equivalent to no voltage. Okay, so if it's a continuous one or continuous zeros, either there is a DC level, either there is a DC voltage, or there is no voltage. Again, this will lead to a problem. So I need a waveform which will have clocking information present. So instead of transmitting NRZ, if I am transmitting RZ, even if there is a continuous string of 1, the condition is that it should occupy only half the bit period. So after half the bit period it will come to 0, and therefore there will be clocking information present. Okay, so this is very important. Without clocking information, I will not be able to demodulate received information. The third is bandwidth occupied. If the signal is occupying more time, it's going to occupy less bandwidth. Okay. On the other hand, if it's occupying less time, it's going to occupy more bandwidth. So if it is occupying more bandwidth, then on a bandwidth constrained channel, I will not be able to transmit this information. On the other hand, if it is occupying less bandwidth, I will be in a position to transmit this information. Now let us try to find the bandwidth of this signal. Now this is I am taking the spectrum of NRZ waveform, NRZL. So let us try to find the bandwidth of this. Now on this spectrum, you see this is the 6th spectrum. The first null is occurring here. So this first position of this first null approximately gives me the occupied bandwidth. Now let us move the marker. So this is about 253 kilohertz. Okay, so 253 kilohertz is NRZ waveform. Now let us compare this waveform with RZ. Remember, in time domain, NRZ occupies larger time, RZ occupies less time. So NRZ occupying more time would have lesser bandwidth, and the one which is occupying less time will have more bandwidth. So let us now look at RZ signal. Just note down that the marker position for NRZ signal is at 253. The first null is happening at 253 kilohertz. Now let us move this to RZ waveform. RZ waveform also has a DC component because it is unipolar RZ. So if it's unipolar, there is an average DC value present. So there is a DC component, and the position of the spectral null is now somewhere there. So it's 478 kilohertz. So it is occupying much more bandwidth, which is expected because RZ waveform occupies less time, so it has more bandwidth. It occupies more bandwidth, and therefore, if I have a channel which cannot accommodate this bandwidth, I will not be able to transmit this information over that channel. Because if I try to transmit this information, I am going to have, the channel is going to act as a band pass filter. It's going to clip all those frequency components which lie outside the bandwidth of the channel, and therefore this signal is likely to get distorted when it reaches the receiver. So I will not be able to transmit this information on a channel which is having a bandwidth which is much smaller than the signal's bandwidth. So this is the way, by spectrum analysis, using a spectrum analyzer, I will be able to find out the properties of line code. For example, this has a DC component. I am looking for a line code which does not have a DC component. So let us check few more line codes and see their spectral characteristics, specifically with respect to the DC component. Now this also has a DC component, though it's small, it's quite small, but still there's a DC component. Now this is biphase L. What I am showing you is the spectrum of a biphase L. This also has certain amount of DC component. alternate mark inversion, the spectral characteristic, this also has a DC component. A very small DC component. If it is a small DC component, it is okay, I can still propagate it. You can almost say there is no DC component because it's a small value, but still, but there is no DC component for this biphase L. Okay. So this is the way I should characterize a line code. See its time domain characteristic on the oscilloscope, see its spectral characteristic, and decide which line code is suitable for a given specific purpose. So the previous demonstration was on line codes. Now line codes basically are the baseband data. Now if you want to pass this baseband data on a baseband channel, it may transmit. But if the channel happens to be a band pass channel, then the channel will not accept your baseband data. Then what should I do? I must look for a carrier with which I can suitably transmit this information. So I must use a carrier, modulate the amplitude of a carrier or frequency of the carrier or the phase of a carrier. Now in this case, the baseband data is a digital waveform, a rectangular waveform. Therefore, the corresponding digital modulation schemes are the ASK, FSK and PSK. Now ASK, FSK and PSK are called amplitude shift keying, frequency shift keying and phase shift keying. So ASK, FSK and PSK are your digital analogs of amplitude modulation, frequency modulation and phase modulation. The modulation scheme is similar. The only difference between the two modulation schemes is one is analog modulation, this one is digital modulation. The baseband data there was analog in nature, the baseband data here is digital in nature. So now we will demonstrate to you the digital modulation scheme. Now again, just as in the case of analog modulation, I require a message signal, I require a carrier, I need a modulator. The message signal here is in a digital form, so these are the line codes. Now I am going to use a modulator and modulate a carrier with these line codes and transmit this. By modulating the carrier with these line codes, this signal becomes a band pass signal and therefore this can be transmitted over a suitable band pass channel. Now I am going to use the same kit which you saw last time where I had generated the line codes. Now this kit also has a small section which can generate the carrier. Now there are three carriers here marked sign 1, sign 2 and sign 3. This is sign 1, this is sign 2, this is sign 3. Now sign 1, let's measure this on the oscilloscope. So the carrier frequency is 2 megahertz. Okay, so this is sign 1. Let's measure sign 2. There is some distortion. Right. So this is 1.003. So 1 megahertz. Sine 2 is 1 megahertz. Sine 1 is 2 megahertz. Sine 2 is 1 megahertz. Let us measure sine 3. Sine 3 is also about 1 megahertz. Okay. So I have three carriers here, sine 1, sine 2 and sine 3. Now using these three carriers, I will transmit information by ASK or FSK or by PSK. For amplitude shift keying, I just need one carrier. So let us use 2 megahertz carrier and try to send this information. Just a word of caution. You see this again, using our usual notation, this lowermost trace is the clock information The middle one is the actual data and the top one is a modulated signal. Now in amplitude shift keying, I can send a 0 as such, but I am sending a 1, I can send the carrier. So when the carrier is on, it means I am transmitting a 1. When the carrier is off, I am not transmitting any carrier. Okay, so that when the carrier is off, I am transmitting a 0. So notice in this waveform, this is binary 1, so the carrier is transmitted. This is binary 0, there is no carrier. Again this binary 1, the carrier is transmitted. So this is amplitude shifting. One thing that I want to note, I want you to note here is on the oscilloscope the carrier is appearing as if it's a square wave. In general, this is not correct. There is some clipping in the circuit because of which it is appearing as a square wave, but what I have used is a sinusoidal carrier. Okay, so this is actually sinusoidal carrier with some clipping on it. So the important thing to realize here is in amplitude shift keying, when I am transmitting a 1, I will transmit the carrier. When I am transmitting a 0, I don't transmit any carrier. So this is how ASK signal will look. Now I can, apart from transmitting the amplitude of the carrier, I can also modulate the carrier's frequency. Now in the case of frequency modulated signal, the carrier frequency was continuously modulated. In the case of digital signals, because the baseband signal has discrete levels, a 0 or 1, my carrier will switch between two frequencies. When I am transmitting a 0, I will use one frequency. When I am transmitting a binary 1, I am going to transmit another frequency. Okay? Now whether I use a lower frequency for 0 or lower frequency for 1, that is immaterial. What is important is I must use one frequency for one bit and another frequency for another bit. So when I am sending a 0 and 1 individually, I may use two frequencies. Now I can also club bits into what I call as a symbol. If I put two bits together, I call it as a symbol. So 0 0 is a symbol, 0 1 is a symbol, 1 1 is a symbol, 1 0 is a symbol. Now there are four symbols. If I want to transmit these four symbols using FSK, I will need four different frequencies. One frequency to transmit a 0 0, one frequency to transmit 1 0, one frequency to transmit 0 1, and yet another frequency to transmit 1 1. So I will need four frequencies. If I have a larger number of symbols, I will require a larger number of frequencies to transmit those symbols. So here, this is an example of what we call as binary frequency shift keying. That is, I have only 0 and 1. I use one frequency to transmit a 0. I use another carrier frequency to transmit a binary 1. So here, let us look at the waveform now. Remember, sine 1 was 2 megahertz, sine 2 is 1 megahertz. So I am going to use 2 megahertz to transmit a 0 or a 1 and 1 megahertz to transmit the other bit. So here I am going to transmit by FSK. So you notice very distinctly, you see the 0 is being used, I am using a low frequency. For a 1, I am using a high frequency. For a 0, I am using a low frequency. For a 1, I am using high frequency. Okay? So this is the way I transmit information using frequency shift key. So this is very important for you to realize. If the baseband data was analog in nature, I will have normal FM that we have already seen. If the baseband data is digital in nature, I will have abrupt shift in the frequency of the oscillator, and therefore I will have high frequency to transmit in 1. I could have also used high frequency to transmit a 0 and low frequency to transmit a 1, it doesn't matter. Okay? What is important is these two bits are distinguished by two distinct frequencies. That is very important. Next, I will show you phase shift keying. So we have already seen amplitude shift keying. We saw just now frequency shift keying. The third kind of modulation, the phase shift keying, is what we will demonstrate. I will show you all these things on time domain right now, and then we will go to frequency domain and we will see how the spectrum of each of these signals should look like. Talk about phase shift keying. When I am transmitting a 0, I may use a carrier without any phase shift. When I transmit a 1, I may use a carrier with phase shift of pi. So, what now happens is, when I am transmitting a 0 followed by a 1, you will see a phase change of the carrier. In one situation, when I am transmitting a 0, there is no phase change. When I am transmitting a 1, there will be 180-degree phase change in the phase of the carrier. So here, Now this is my clock information, this is the baseband data, this is the modulated signal. Again it is appearing as square wave, it is actually a sine wave, but because of some problem in the circuit it is showing as clipped circuit, and so it is appearing on the oscilloscope as a square wave. Now notice, this is a binary 1, this is a binary 0. So I am going from a binary 1 to binary 0, there must be a phase transition now. If you see carefully in this signal, there is a phase transition here. So I am going from high state to low state to low state, so there is a 180 degree phase shift. If I increase the timeliness of the signal, you will see wherever there is a transition from 1 to 0, there is a phase shift. There is a transition from 0 to 1, there is a corresponding phase shift. Okay, so wherever there is a change of bit from 0 to 1 or 1 to 0, there will be a phase shift in the phase of the carrier. This is basically PSK. So if I want to demodulate PSK, I just have to sit and monitor the phase of the carrier. The phase of the carrier changes its phase, I know that there is a change in the bit. It could be a 0 or it could be a 1. Okay, so this is basically PSK. So on a given channel, I can either use amplitude shift keying, I could use phase shift keying, I could use frequency shift keying. Out of these three modulation schemes, frequency shift keying is not bandwidth efficient, because for each additional symbol that I am trying to transmit, I need additional frequency. So I'm going to, in a given channel, I'm going to consume all the possible frequencies. This modulation scheme is not bandwidth efficient. Okay, so this is very important for us to understand. Now, having seen the digital signals in time domain, let us now see the spectral characteristics. Let us first go to amplitude shift keying. Let us try to first understand what should happen. In amplitude shift keying, I used only one carrier, that was at 2 MHz. Okay? Remember that the baseband data is rectangular in nature. So it is obvious that the power spectrum should appear as sinc square spectrum. But where should the center of the sinc square spectrum be? It should be around the carrier frequency. So I'll expect a sinc square spectrum to be located around 2 MHz, because 2 MHz is the carrier frequency. Let us see that on the oscilloscope, on the spectrum analyzer. So now I have connected the same kit that generated all the digitally modulated signals which we saw in the time domain. I connected the same kit to the spectrum analyzer now. The first spectrum that I am trying to show you on the screen is that of an amplitude shift key. Remember, I told you that I am choosing a carrier with a frequency of 2 MHz. The sinc spectrum has to be centered around 2 MHz. What you see on the screen is basically the sinc spectrum, and this is located at 2 MHz. Okay? So why is it sinc spectrum? Is because your baseband signal is rectangular in nature. Because it's rectangular in nature, the spectrum will be a sinc square spectrum. But since I am putting in a carrier of 2 MHz, this sinc spectrum will be now located centered around 2 MHz, to the 2 MHz. Now let us next go to frequency shift key. Let us see the spectrum. What do I expect? The spectrum will still be a sinc squared spectrum, but there will be two peaks, one for 1 MHz, the other for 2 MHz. Remember, I am using two carriers here, one at 1 MHz, the other at 2 MHz. Now let us look at that. Notice another peak coming up here. Okay, this is a 2 MHz peak, this should be a 1 MHz peak. Let us move the marker and verify. Yeah, look at that, it's 1 MHz. So there are two carriers here, one is transmitting a 0, the other is transmitting a 1. So I use 2 MHz carrier to transmit one bit and 1 MHz carrier to transmit the other bit. This is what frequency shift keying was, which is very beautifully shown on spectrum analyzer. This is a 2 MHz peak transmitting one of the bits, this is a 1 MHz peak transmitting the other bit. Okay, so this is how the FSK spectrum should look like. The basic nature of the spectrum will still be sinc square, except that there are two carrier frequencies here, so the sinc square spectrum will be centered around two carrier frequencies. If I have multiple carrier frequencies, if I were having more symbols to transmit, I will have more number of peaks. Each of those peaks will be, each will be a sinc square spectrum which will be centered around that particular carrier frequency. Okay, so this is should be clearly understood by you all, and this is very beautifully shown on the spectrum analyzer. Next, let us go to phase shift keying. In phase shift keying, I am using only one carrier. I am only changing its phase. I am not doing anything else to the carrier. Okay, I am only changing its phase. I am using no phase change for the carrier as such to transmit one bit, and a phase change of 180 degrees to transmit the other bit. Okay, so this is binary phase shift key. I am transmitting binary information using phase shift key. Okay, so this is binary phase shift key. So if I connect a BPSK signal to the spectrum analyzer, I'll expect only one peak, and that one peak will be located at 1 megahertz. Okay, I'm using a 1 megahertz carrier. Okay, now the phase information that is present in BPSK signal will be lost. Why? Because on this spectrum analyzer, I am measuring only the magnitude spectrum. I am not measuring the phase spectrum. To measure this phase spectrum, you will require what is called as a vector analyzer, okay, a network analyzer, which will give me both magnitude as well as phase. The phase information here is lost. I'll only see a spectrum centered around 1 megahertz, a sync square spectrum centered around 1 megahertz. Let us verify that. Right? That's a sync square spectrum located at 1 megahertz. Okay, so the phase information is lost. I'm only having the magnitude information. I'm using a carrier of 1 megahertz frequency, and therefore this spectrum is located around 1 megahertz. So this is the way we will analyze the digital signals, the time domain representation and the corresponding spectral representation.